All right, so with that, today we're going to talk about pH and acid-base equilibrium. So just as a reminder to us all, that pH is the negative log concentration of H plus or H3O plus, right? Okay, so again, that's helping us out with that. All right, so let's go forward then. And there is a set of notes for this in Schoology that you can go ahead and print out or use, etc., as we work through these. All right, so today is all about calculating pHs depending in strong acids, strong bases, weak acids, and weak bases. All right, so for the situation where we have strong things, the calculating of the pH is very easy. For any monoprotic strong acid, the concentration of H3O plus equals the concentration of the acid. And so then you just go ahead and use pH formula with that. H2SO4, which is diprotic, is a little bit more complex. So we'll talk about that a little bit more, how we deal with H2SO4 a little bit later. All right, so as an example, what is the pH of a 0.040 molar solution of HClO4? All right, so step one, go ahead and calculate the concentration of the acid. So since it's a strong monoprotic, that's the molarity of the acid. So in this particular case, the concentration of H plus is 0.040 molar. Okay. Second, we're going to go pH equals the negative log of the H. Okay, so pH equals negative log 0.040 molar. And if we run that through our handy dandy calculator, we get 0.040. Okay, this has two sig figs in it. So that means that we get two numbers after the decimal in the pH because it's a logarithmic. So two numbers in the mantissa. Okay, for strong bases, it's the situation very similar. The concentration of the OH that we would use is the concentration of the base. And the only thing that's a little bit tricky here is that we have our alkaline earth metal strong bases where we get two OH ions out of every single molecule. And so as a result of that, the concentration of the OH is going to be double the concentration of the base. All right, so here's our example. What is the pH of a 0.028 molar solution of NaOH? Okay, so calculate the concentration of OH. So this has only one OH per molecule. So that means that the concentration of this is going to be 0.028 molar, right? And calculate POH. It's going to give you the negative log of 0.028 molar. Okay. And go ahead and do that, and we get a POH of 1.55. So then to go to pH, we of course go 14 minus POH, so 14 minus 1.55, and you get a final answer of 12.45. Let's do one more. Okay, so what is the pH of a 0.0011 molar solution of calcium hydroxide? So in this case, we get two hydroxides out of every single one. So it's going to be 0.0011 molar times 2. So the concentration is 0.0022 molar. Okay, so then we go POH equals negative log of that. Okay, which gives me a POH of 2.66. All right. So then to get to pH, we're going to go 14 minus 2.66, which should give us an answer of 11.34, which indeed it does. Okay. Okay, so now we're going to move on to weak acids and weak bases. And so remember, the difference between a strong acid and a strong base and a weak acid and a weak base has to do with the amount of dissociations. We assume that a strong acid and a strong base will completely dissociate. So essentially, you have a dissolution that goes to completion. Whereas with weak acids and weak bases, you end up with an equilibrium situation. So your weak acid plus the water in the solution is going to give you your anion as well as H3O plus in an equilibrium setting. So if we write the equilibrium expression for this, of course, liquids don't go into it, so the water won't. We get products over reactants. So H3O plus plus the anion all over the weak acid. And that's our equilibrium expression for this. Okay. That equilibrium expression, Ka, again, is essentially telling us how much of the weak acid dissociates. So the bigger the value of Ka, the stronger the acid, because more of it is dissociating. Okay. So since it's an equilibrium situation, we can go ahead and we can calculate Ka from pH or vice versa, because concentration of H3O plus is part of our equilibrium expression. And of course, we would know what Ka is. So here are the steps to calculating Ka from pH. First thing, I'm going to set up a rice table. We're going to set the initial concentration of HA being the molarity given, and then assume the initial for both of our products is 0. Calculate the H3O plus at equilibrium from the pH, which they'll give us. You can put that into your equilibrium table or your rice table then, and figure out what X is, and then go ahead and write your Ka expression and plug things in. So there's your steps. Let's go ahead and let's do one. All right, so here we go. Student prepared a 0.10 molar solution of formic acid and found its pH at 25 degrees Celsius to be 2.38. Calculate the Ka for formic acid at this temperature. All right, so let's go ahead and put in our rice table. Okay, and we're going to start off with, we have HCOOH, and that's going to go to H3O plus COOH minus, okay? Or we could just say H plus here as well. It doesn't really make a difference. Okay, so our initial concentration, they told us the formic acid itself is 0.10 molar, so that's what I put there. We assume we have 0 of those to begin with. Okay, by the stoichiometry, this is going to be minus X, this is going to be plus X, this is going to be plus X, okay? And then they also told us here that our pH is 2.38 of the solution. Okay, so that's going to give me allow me to figure out my equilibrium concentration of H3O plus. So concentration of H3O plus is going to be 10 to the negative 2.38, okay, which equals 0.0042 molar. Okay, so I'm going to go ahead and put that in there. 0.0042 molar. Since this is plus X, that means, and it started at 0, this also has to be 0.0042 molar. And that means over here we are going to be subtracting 0.1 minus 0.0042, and that gives me 0.096 molar. All right, so we got that going on then. So the next step that we have then is, since we're trying to calculate Ka, Ka is products over reactants. So this is going to be H3O plus times COOH minus over HCOOH, which therefore equals 0.0042 times 0.0042 all over 0.096. This gives me a Ka then of 1.8 times 10 to the negative 4th. Which indeed it is. All right, so when we do rice calculations, you guys know that there are occasions where we will assume that the change is much less than the initial concentrations, and so we can make some assumptions. And so percent ionization is something that helps us do that. It is another measure of acid strength, and it's a way of calculating, in order to calculate percent ionization, we're going to use this. So we're going to go ahead and we're going to, percent ionization is the H3O plus concentration at equilibrium divided by the initial concentration of the weak acid times 100. Okay. So as an example for this, we're going to go ahead and we're going to use that last problem that we did, and we're going to get percent ionization is going to equal the concentration of H3O plus over the initial at equilibrium over the concentration of formic acid initially times 100. Okay, and if that's the case, we get 0.0042 divided by 0.10 molar times 100. And in order to get, what did we do that? We get a percent ionization of 4.2%. All right, awesome, fantastic. Okay. And indeed it is. So when does this become useful? Well, it becomes useful when we have to run this thing the opposite way, which is calculating pH from Ka. Right? And so our way of doing that then is we go ahead, set up a rice table. The initial HA is the molarity given. We assume 0 for our products. We set up our Ka expression. We simplify that if the percent ionization is small, which we use either something called the 20 times rule or the less than 5% rule. So as long as the ionization is less than 5%, or the difference between Ka and the concentration is 20%, we can assume that X is negligible compared to the overall concentrations. We've done this before. It'll be familiar once we do the table. We're going to solve for X and fill in the other rice values, and then finally use H plus to calculate pH. So let's do it. All right, so we're going to calculate the pH of a 2 molar solution of HCN, and they give us the Ka of that. So rice to begin with. So HCN, H plus CN minus. Okay. Initial concentration, 2.0 molar from the problem. These we assume to be 0. By stoichiometry, this is minus X, this is plus X, this is plus X. And so we get 2.0 molar minus X, X, and X. All right, so at this point, we look at this and we say, all right, Ka is 10 to the negative 10th. We are dealing in 10 to the first. That's definitely way off. So I'm going to go ahead and we're going to assume that even at equilibrium, the HCN is not going to change much. It will still be 2 molar. All right, so let's go ahead then. Once we've got that, we can go ahead and do our Ka expression, which is H plus times Cn minus all over the concentration of HCN. Okay. All right. So with this then, we can go ahead and plug in. Ka is 4.9 times 10 to the negative 10th equals X times X all over 2, or X squared equals 9.8 times 10 to the negative 10th. Take the square root of both sides, and we see that X ends up being 3.13 times 10 to the negative 5th, or with sig figs, 3.1 times 10 to the negative 5th. Okay, so that then gives us our X, right? And X is the concentration of H. So from there, we can go ahead and we say pH is the negative log of the concentration of H, which is the negative log of 3.1 times 10 to the negative 5th. And that means that our pH equals 4.51. Okay. All right, so let's validate our assumption. Negligible means less than 5%. Okay, so we're going to go back and we're going to say All right, so our equilibrium concentration of H plus was 3.1 times 10 to the negative fifth. Our initial concentration was 2.0 molar. Multiply that by 100, and we get 0.00155%, which is way less than 5%, so our assumption is valid here. All right, so one interesting situation that happens with weak acids is when you have polyprotic acids. We've talked about these before. Monoprotic acid gives off one hydrogen ion, diprotic. 2, triprotic. 3, we refer to polyprotic as anything that is di or triprotic. All right, so because they're giving off one hydrogen, or giving off hydrogens, they don't all go off at the exact same time. You remove one, then you remove a second, then you remove a third. All right, and so as a result of that, there's an equilibrium constant, or acid dissociation constant for each proton that comes off. And so you can see down here on the table on the bottom that as you get to each successive proton being taken off, the Ka gets smaller and smaller and smaller, which is what you would expect, because as you remove a hydrogen, it's going to be harder to remove the next hydrogen and harder to remove the hydrogen after that because of the attractions that are involved. So again, each proton gets harder to remove, so Ka2 and Ka3 are usually very, very small. So if you're doing calculations with polyprotic acids, does this mean that you have to use 2 ice tables in order to be able to figure out things like Kas or figure out things like pHs? No, because as long as the successive Ka values differ by 10 to the third or more, you can just estimate the pH using Ka1, because the additional protonization that comes on after that is not going to change the overall concentration of the hydrogen ions very much at all. It's just going to be a tiny bit, and it's going to be not significant or insignificant compared to the first one that comes off. Right? So one thing that happens here as you think about this is you get H2SO4, and it can be viewed as a monoprotic strong acid forming HSO4 minus. So the strong acid reaction with sulfuric acid is H2SO4 goes to H plus HSO4 minus. All right, so let's do an example. The solubility of CO2 in water at 25 degrees Celsius and 0.1 atmospheres is 0.0037 molar. The common practice is to assume that all of the dissolved carbon dioxide is in the form of carbonic acid. What is the pH of a 0.0037 molar solution of carbonic acid? All right, so we're going to do this just like we have before. Here's our rice table. H2CO3 goes to HCO3 minus plus H plus. All right, so there's our initial thing. So I'm going to go up here to the carbonic acid line here, and I will see that the first deprotonization, which is the one we just did, has a Ka of 10 to the negative 7th. The next one has a Ka of 10 to the negative 11th. Those are more than 10 to the negative third apart, so we can just go ahead and assume that all of the important equilibria for determining the concentration of H is going to be based off of that first equilibrium constant. All right, so initially they told us that this is 0.0037 molar. We know that this will start at 0 and 0. Based on concentrations, this is minus x plus x plus x for the stoichiometry. Which then gives us 0.0037 molar minus x and x and x. All right, so they want to know what the pH is. We've got to figure out the concentration of H. Okay, so once again, we see that the Ka here is about 10 to the negative 7th, and right now we're at 10 to the negative 3rd. That's probably going to be a difference of at least 20 times or less than 5% ionization. So for right now, we're just going to make the assumption that this is 0.0037 molar. Okay, so Ka equals the concentration of H plus HCO3 minus over the concentration of H2CO3. Substituting in for that, then, we know that the Ka1 is 4.3 times 10 to the negative 7th. We know that that's going to equal x times x all over 0.0037. Okay, so x squared then equals 1.6 times 10 to the negative 9th, which then means that x equals 4.0 times 10 to the negative 5th. Okay, so that's my H plus then. So that's going to help me out then. pH equals negative log concentration of H plus, which equals negative log 4.0 times 10 to the negative 5th. 4.40, which indeed it is. All right, so weak bases work a similar way. Weak bases are going to react with water to produce hydroxide ions, setting up the equilibrium situation as described here. The most common weak base we encounter is ammonia, and it's just one to always remember that when you have ammonia in water, you are going to end up with a weak base situation where the ammonia is the base, picks up a hydrogen and gives you the ammonium ion, and the water picks up or loses the hydrogen ion, and so you end up with the conjugate base of hydroxide. Okay, so that means a solution of ammonium hydroxide is really the same as ammonia. Some other key common weak bases are amines. Amines are compounds that have a nitrogen with 3 single bonds and a lone pair of electrons. So methylamine, ethylamine, those were both examples of that. Diethylamine, trimethylamine, all of these, right? They all have an N with 3 bonds and a lone pair with them. Ammonia is an amine, okay, NH3. We also have pyridines. Pyridines are a hydrocarbon ring, a benzene ring, that has a nitrogen ion on one vertex, and therefore it has lone electrons up there. And that's another common weak base. It could have other functional groups that hang off the sides here, but the situation here is such that we have this, and this is called a pyridine. The last one is a conjugate base of weak acids. So we can generate these by just simply dissolving ionic salts. So like a carbonate or a hypochlorite. All of those are things that we can go ahead and dissolve. And so as a result of that, you end up with those being conjugate bases of weak acids. Because if you add a proton to them, you get the species described over here. Okay, so for weak bases, again, here's our equilibrium. And we can then therefore write an equilibrium expression called the base dissociation constant, or Kb, for that, which is Hb plus OH minus goes to B minus. Okay. So calculations using Kb. With Kb, you can find OH, and then through that, you can use the relationships that we've learned to figure out what pH is from there. So how would you do this? Well, you would go ahead, Rice table, given the initial molarity is the molarity given, 0 for the products, set up your Kb expression, simplify it if percent ionization is small, solve for X, that gives you OH, and then use OH to calculate POH and pH. So let's go ahead and give this a try. What is the pH of a 0.15 molar solution of NH3? Okay, so here's our reaction. NH3 plus H2O goes to NH4 plus OH minus. Okay, water is water, so we don't really care about that. But our initial concentration here of ammonia is 0.15 molar. The initial concentration of the products is 0. The change based on stoichiometry is going to be minus X plus X plus X, okay, which gives me an equilibrium of 0.15 molar minus X and X and X. Okay. Now from a table, we can see that the Kb for our reaction is 1.8 times 10 to the negative fifth. So I'm going to go ahead and add. We know that from the equilibrium expression, that's going to be NH4 plus OH minus all over NH3. Okay, so given that, then we can go ahead and do our calculations. This we're going to assume is 10 to the negative fifth, and we're operating in 10 to the negative first land here. And so we're going to go ahead and just assume that that's going to be 0.15. We'll check that assumption later on. So KB equals 1.8 times 10 to the negative fifth, which equals X times X over 0.15 molar. Okay. That means X squared is equal to 2.7 times 10 to the negative sixth. That means X is going to equal 0.0016 molar. Okay. All right. So that means then that POH equals negative log of the concentration of OH, okay, which equals negative log of 0.0016. So POH is going to equal 2.80, which means pH is going to equal 14 minus that, which gives us 11.20. All right, to justify this, we can look, and we'll see that the concentration of OH was about 0.0016 relative to the initial concentration of 0.15 molar. That's about 1/100th of that. So again, way less than 5%. So again, our justification of simplifying and just using 0.15 rather than 0.5 minus X was justified. All right, so last thing we have is the relationship between Ka and Kb. And so we have seen this chart before where we have stronger acids have weaker conjugate bases. We see that qualitative chart there. And we see that we want to know, can we quantitatively evaluate the strengths of acids and bases? And we can by comparing their Kas and their Kbs. If Ka is greater than Kb, then the acid is stronger than the base. Okay, if Kb is less than Ka, Ka is less than Kb, then the base, of course, is stronger in relative. Because Ka represents an acid dissociation and Kb represents a base dissociation, putting them together would give us the constant for the dissociation of the ionization of water, Kw. Okay, right? Combining equations requires to multiply equilibrium constants, right? And so if we look here, that means that Ka times Kb is going to give me Kw. Okay, and we know that Kw is 1 times 10 to the negative 14th at 25 degrees Celsius. So if we know one of the pair, we can find the other. So if someone gives us a Ka, we can figure out the Kb. If someone gives us the Kb, we can figure out the Ka. All right, so it says, calculate the Kb for the fluoride ion. For HF, the Ka is 6.8 times 10 to the negative fourth. So we can think of this as HF goes to H plus F minus. Okay, so that means the Ka is going to be for the forward reaction. The Kb is for the reverse reaction. Okay, we know that Ka times Kb equals Kw. We're going to assume we're at 25 degrees Celsius here. All right, so Kb is going to equal Kw over Ka. So we've got 1.0 times 10 to the negative 14th over 6.8 times 10 to the negative 4th. And that's going to give me a Kb for the fluoride ion of 1.5 times 10 to the negative 11th, which indeed it is. All right, so the last thing then is, since we know that Ka and Kb equals Kw, and we know that Kw is 10 to the negative 14th, we know that logarithmically we can change these all into P. So we know that pKa plus pKb is going to equal 14, and we can use that sometimes when it's useful as well.